Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great honor to have Henry Thompson here from Edinburgh, actually, we were talking before here, there actually is a historical connection between computational linguistics and data collection efforts and XML and W3C and all this. I don't know that Henry's going to describe any of those historical connections, but they're probably the reason he's here. So without further ado, let's hear from Henry.
Thank you. I've just now got to find my slides.
Oops. Maybe I should have had a little more to do.
Oh, no, I just realized what I did wrong. Somewhere in here. One of these.
Oh, and just on various details.
There we
I
are.
think we have the room technically for an hour and a half from 9.
Right.
But, usually the talk kind of go for an hour.
Yes. My goal... So thank you, Ken, and thank you all for coming at this ungodly hour of the morning. I'm time shifted from the UK, so it's sort of the middle of the afternoon for me. Hello, Bob. It really is old home week. Ken and Bob and I were all sort of post-grads together in the deep, dark, distant past, slightly before God left Chicago. So as Ken mentioned, I started out as a linguist and a computational linguist doing grammar and knowledge representation and things like that at Berkeley and at Park in the 70s. And via a trajectory which I won't bore you with, for the last 7 or 8 years I've actually been working mostly on foundations of web technologies, XML in particular, XML and related technologies. But what I want to do today is actually give you a sampler of 4 different areas where specific aspects of linguistics, computational linguistics, philosophy of language are actually were research questions that matter on the web. Matter for web technologies, actually benefit from input from good old-fashioned disciplines in the general space that I'm indicating, where there are real scientific research problems, the solutions of which can have a direct impact on how the web works and how it prospers. I'm not going to talk about the sort of structural and social and political issues, since in general one of the major problems that I've had over the last 10 years or so that I've been playing this game of trying to take various aspects of computer science and linguistics and so on into the web standards business is that when you're sitting in a standards development meeting and a bunch of people around the table, all of whom made their first million before they were 13, and write code with both hands and both feet, and have egos the size of the planet, say that they think that they're going to proceed in the following way, and you sort of stick your hand up and say, well, actually there's this result which proves that you can't do that. You don't really usually get a very satisfactory response, right? That's just not a viable way to proceed. So getting the science into the standards process, into the products, well, getting them into the products is something you're all more familiar with than I am, but that sort of impedance matching communications problem is not something I'm going to talk about. I figured here today what I want to do is interest you in the science, if I can, is talk about some of the science. So there's this new journal called Web Science or something like that. As Ken is absolutely right in the discussion we were having just a minute ago, that what this indicates is that there must be money here somewhere. Whether there's science here or not is a separate question. But as I said, there are some real scientific questions. Should I bump the point size up 1? Is this okay from the back? You're all young and fit. And I've got it right here. So I'm going to look at 4 examples. The first is perhaps the most timely. I don't know how much you guys are aware over here of the controversy about the future of HTML and the relationship between the future of XHTML, that is HTML, which is XML well-formed, and old-fashioned HTML, and the mess that's out there on the web, which is largely neither of the above. But this topic area starts with a joke, which is, the question is, what do Lenin and Tim Berners-Lee have in common? And the answer is, both of them have had to admit that the withering away of the state, or HTML as the case may be, will be indefinitely postponed. What this refers to in the web context is that 4 or 5 years ago, when XHTML was launched, the W3C's official stated position was, XHTML is the future of HTML. It will come to replace HTML. Our goal is that all HTML will in the future be XHTML. We do not intend to develop HTML itself as such ever again. All development, elaboration, improvement, bug fixes, etc. will be done in the XML line. Well, it hasn't worked, has it? There's this effort which is started out outside the W3C and has been embraced and extended by the W3C, moved into the HTML working group to produce HTML next, HTML5, whatever it's going to be called, in a way which doesn't rule out the indefinite persistence of not just HTML, but broken HTML, tag soup, junk, which has a few indicators in it that its authors intended it to be interpreted as HTML, even if most of it is sort of arbitrary nonsense. I sit on the technical architecture group of the W3C, who are not chartered to deal with this problem directly, but are concerned to try to understand what the fundamental architectural issues are that are raised by, shall we say, can we have the web go forward with both tag soup HTML and well-formed XHTML? What does this mean? How do we do this? All right. The key points in that is that tag soup is going to be tolerated, and in particular browser error recovery, which those of you who remember, the original motivation for XML was to short-circuit one aspect of the browser wars, which was each of the browser manufacturers trying to duplicate the other's error recovery strategies. And the idea was, no, XML is much simpler. XML has a halt and catch fire story. If it's not well formed, you don't do anything with it except say, please try again. Right? Well, that didn't work. And the error recovery strategies have established a de facto standard for what can and can't be displayed on the web. And what's interesting about this from a sort of formal language theory perspective is that the position of most of the leading lights in this let's standardize what the browsers do and call it HTML5 position is that they will not provide any formal definition of what it is that they are going to accept. Right? No schema language is adequate for describing the conformance languages, the conformance requirements for XHTML5. XHTML5 means no formal schema, right? No grammar. At the same time, these very same people are writing schemas, they just don't want them to be official. All right, I'm going to skip over the background here because this isn't really what's interesting. So, this is, well, we'll see if this breaks or not. This is one of the external references. So what the working group is currently doing is producing this. This is actually today's version. Hixie's been busy this morning. And here's an extract from the official normative definition of what you can and can't do. It's a bunch of my programming language, as we used to call it, right? Sort of semi-formalized English of a procedural sort, which says, if the head element pointer is null, switch the insertion mode to before head, otherwise yada, 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 with gotos and everything else, right? So is this really the best we can do? Do we really want this to be the normative definition of what the next generation language is for the web? Well, gee, I really hope not, right? And so I've been looking around at what the alternatives are. There we go. So possible starting points for a formal definition of vNext for HTML. Well, the browser error recovery is formal. It's in some programming language or some different sets of programming languages. But it's a little hard to extract generalizations from or to actually pin down. Many of you will know of Dave Raggett's HTML tidy tool, which takes pretty arbitrary tag soup and produces clean HTML or clean XHTML, depending on what flag you give it. But again, it's a bunch of code. It's relatively well-structured code, but it's a bunch of code, and it doesn't have any declarative formulation. What you may not know about is work done by a gentleman named John Cowan, who used to work for Reuters, recently went to work for Google, which is called tag soup. Tag soup is a modest program which takes arbitrary character sequences, actually, as input, and does its best to produce well-formed XML as output. Obviously, the closer the input is to XML, the more likely it is that the output will be what you expect it to be. But it will take anything at all and produce well-formed XML from it. It's slightly biased towards consuming and producing things which are close to XHTML, but it, in principle at least, will work with any XML language. It has two phases, tokenization and what John calls rectification. And they're what you would expect, basically. The tokenizer is an error recovery, a tokenizer with a bunch of error recovery built into it. And rectification is something that takes the token stream and tries to turn it into XML. Both phases are table-driven. The tokenization, well, I'm going to skip over this for now. But here's an example. Consider the following. The last time I gave this talk was in Canada, so the examples are taken from there. Consider the following broken XML, where we have tags that cross legs, right? Looks like that. The tokenization output looks like this. This is a format called PIX, developed originally by Sean McGrath. It's a sort of XML updating of the old ESIS output of SGML. But you can basically read it as one line per token. The kind of token is indicated by the first character, and the content of the token is given by the rest. And open paren means start tag, and hyphen means text content, and close paren means end tag. Right? So there's the tokenization of that document. It's still got crossed legs in just the way you would expect. Whoops, that's not what I meant to do. And here's the rectified output, in which the offending crossed legs have been removed, but the overall rendering effect will be preserved by inserting first a close B tag before the original close I, and then a new open B tag to resume the bold after the italic ends. And the HTML looks as you would expect it to. But tag soup is not a perfect solution to our problem, partly because for sort of low-level reasons that are corrigible. Its namespace handling is not very good. It treats HTML specially. And you can pretty much do anything you want to improve or change the tokenization by editing the declarative specification, the tables that it works from. But the rectification process is not. There's really no control over what fix-up it does, for instance, over the insertion of those tags, that's accessible other than by fussing with the code. So the classification of errors and the responses to them are hardwired in the program. So the goal of this little exercise that I did a few months ago called PixUp are very similar. That you always produce well-formed output, no matter what the input is. You try to produce well-formed output that's guided by the doc type, by some statement of what the document should look like, but you're not guaranteed to get there. You do your best, but you're not guaranteed. But the crucial thing is that the fix-up controls are also declaratively and externally specified. So you can experiment with changing the recovery and articulating it in different ways. So the architecture is straightforward. It in fact uses the tag soup tokenizer unchanged, and the fix-up phase is, for the time being, just take the token stream and output an improved token stream. Two user-specified declarative resources drive the fix-up: a schema and error recovery specification. The schema is as simple as you can get. It essentially only records vocabulary and immediate dominance. So it tells you who your children are, and that's it. Doesn't tell you cardinality, doesn't tell you order, nothing but dominance, okay, immediate dominance. And it tells you for any given element whether it expects text content or not. That's really still part of immediate dominance. All right. It may include information about preferred parent. So if the same element can appear as the child of multiple parents, and you want to know, well, other things being equal, suppose I had a document that consisted only of this element, what parent ought I to embed it in? Well, you can give me a hint about that, and similarly for text. And it may tell you what elements are allowed to be the root. But it doesn't have to. Those are additional bits of information. So here's a trivial example of what a PixUp grammar looks like. It's just a little bit of XML with one element per element that tells you its name and the names of its children and whether it allows text and whether it might be the root and things like that. Right? So it's very modest amounts of information here. But if you have a large and complex language, you get something like this. This was actually derived semi-automatically from the published schemas for HTML4 and XHTML4, XHTML1. So what do we do with this? Parser works on the token stream. Each rule corresponds to a finite state automaton. Right? Accepting, notice it, because it's parsing the token stream, it takes an open tag token and then some content and then a closed tag token. That's what the parser for the token stream has to do. Right? For example, for the B has C children and may have text, we get an automaton like this. Right? I need an open B token, and then any number of C's and any amount of text mixed together, and then either a closed B token or legacy. PixUp and tag soup allow the old angle/angle anonymous close tag. Right? Close whatever's open, which the Microsoft parsers actually accepted for a little while back in about 1998. Actually, we don't use that automaton because that automaton ends up being non-deterministic in a way that we don't, that's inconvenient. We determinize automaton like that by actually raising the start tag up to the higher level automaton. So for instance, for something which says A can have B or C children or text, it looks like this. Oops, I left the text out. A can have B or C children, not text. An A, assuming we already know it started, needs a start B followed by whatever B accepts, or a start D followed by whatever a D machine will accept, and then a close A. So we sort of shift everything up one, and the machines for a given element don't include the start tag token for that element. This now becomes a deterministic machine, and it makes error detection much easier for reasons that should be obvious. There are essentially 4 ways to lose. There's no more data, but the pushdown stack isn't empty. The pushdown stack is empty, but there's more data. These are sort of obvious boundary cases. There's this sort of odd case, which is this is actually not a tag which I know as being in the language. Right? So there's no rule for this. There's no automaton for it. Or the most interesting case, the current event loses. Right? I've got some token, and I'm in some machine, and there's no transition for this token. What do I do, coach? Right? Well, largely following the sort of the published description of the way tag soup works, the interesting cases are mostly the last case, and we break them down into subcases. So, for example, there's a subcase called upend, which means there's an end tag that I can't consume, but somewhere higher up on the stack there's somebody who could consume it. Right? If we popped some number of automata off the stack, there would be an automaton waiting to take this end tag. Right? So something like this, right? Which is what you typically get in HTML, because SGML allowed you to leave off end tags if it was deterministic how to reconstruct them. Right? So we're waiting for a P end tag at this point, but we don't get one. What we get is an end div. And we can't accept it, but there's a guy higher up on the stack because of this open div who could accept it. Right? Or a bad child, a start tag which isn't allowed here, right? But which is known to have a parent, right? So what are we going to do? The kinds of error recovery for cases like this, there's a vocabulary of actions with respect to the stack that you compose error recoveries from. And the kinds of actions you can perform are discard the current event, output an end tag, insert a start tag, pop the stack, retry parsing the current event, force the current event to be accepted as if there were a transition even though there isn't. And with this language, we can repair all the cases that we know about. So for instance, sorry, we'll skip over this because it's not so interesting. For upend, the answer is output an end tag and pop the stack. Right? So we assume that we get the end tag that we need, we output it, and we pop the stack, and that will then, we hope, consume the closed div. But of course, it may happen several times before we get to the automaton that actually will do the work. Bad child, synthesize, splice in a start tag for this guy. Splice in a start tag for his preferred parent and try again. So that's just a taster of a mechanism that maybe gives us some leverage for this, how to deal with HTML in the wild, tag soup, whatever you want to call it. Some things to follow up if you're interested. Tag soup itself. I gave a longer paper about this in Montreal this summer at Extreme. And there's much more detail about articulating the rule language, both the pattern side and the recovery side, beyond its current toy state. And there's also a modest corner of the formal language theory literature from the 50s and 60s. It doesn't seem to be active nowadays, at least not on the basis of what I could find, concerned with classes of context-free grammars which are repairable with no or finite look-ahead. As far as I can see, this is too constrained to be relevant, but there might be other bits of this literature that I didn't find yet. There certainly, was a time when there were people in the formal language theory community who were looking at error recovery in one way or another, mostly, I think, stimulated by programming language, by parsing programming languages. And there might be more there. I don't know. I'm not, a real formal language theory wizard. Last slide, I think, on this topic. Yeah.
So you do not see the connection to context-free languages?
There certainly is a connection, right? But when I looked at the specific literature that I looked at were the no look-ahead error recovery CFPSGs. What does it mean? What kind of strategies are there? And I looked at various other bits of the error recovery literature. It did not seem to me to apply to the kinds of languages and the kinds of situations that we have in the HTML case. But I could be wrong, and I'd be absolutely happy for somebody to say, hey, actually, this stuff really is relevant. And
the Automata you presented in the stack is exactly context-free language.
It's certainly a context-free language. The kinds of error recovery that appear to be what the browsers do and what people expect given the syntax and semantics of HTML are not the kinds of things that those parsers were doing. Right? Why that is bears further research. I would be happy for somebody to do that. However, right, it's not, there's still a lot of open questions about whether this is worth pursuing, mostly because of script. Right? I mean, there's this profound mess in HTML, which is the fact that you don't actually parse what you see. You parse what you see plus the results of running any script that happens to be interpolated in the middle of your HTML. And so it's perfectly acceptable nowadays, and Microsoft and Google and Amazon and all the big guys do this all the time, to produce HTML which is on the face of it completely broken, because there's script in the middle which synthesizes start tags and end tags and makes everything work. Right? And that doesn't fit with this paradigm very well at all, unless you put a JavaScript interpreter in the tokenizer, which seems sort of backwards. Right? You sort of think, well, I got to tokenize first and then I'm going to, right? But maybe you could do that. I don't know. It's worth looking at. So that was the first example. I should have said earlier, and thank you, questions of clarification always welcome. Short questions about this topic, now is a good time, and then I'll move on to the next topic. Any questions about this one?
Well, so you're outlining a position that would have been very popular when we were in graduate school, and I gather is probably unlikely to win the day today, or am I wrong about that?
I think there is a lot of the people in the HTML working group are frustrated by the fact that the best they appear to be able to do is to produce this 70-page screed of procedural English to define their language. And so if some of the limitations of this approach can be overcome, and maybe they can and maybe they can't, I think they would receive a warm response, a good hearing from at least some of the people in the working group. And how the politics would play out, I can't predict. But I think it's worth exploring. I think there's enough of a chance that it would be worth exploring. Certainly the leading lights have no interest in this. Hixie is just absolutely convinced, Ian Hickson, the editor of the HTML5 spec, is absolutely convinced that nothing but English can do justice to the complexity of the situation. And, not clear whether that attitude will carry the day eventually. There are a lot of people in the working group who are very unhappy with the situation, but they don't know what to do about it. Okay, moving right along. Staying with finite state automata. This is even more heavy-duty formal language theory, but won't last very long. My colleague Richard Tobin did the heavy lifting for the sort of retrospective part of what I'm going to talk about here, and listen to my crazy ideas for the more recent stuff with just the right amount of skepticism. And Michael Sperber McQueen also knows the formal language theory literature, is a big fan of Brzozowski derivatives for solving similar problems, and we sort of played Cox and Box in this area for a while. Just to remind you, if you don't remember, that document structure definition for the sort of markup languages in general, ever since SGML, have used some kind of regular expressions to define their grammars, to define what are called content models. Right? The alphabet is typically composed of element names, and the operators include conjunction, disjunction, and interleave, notated with comma, vertical bar, and ampersand in SGML and XML DTDs, and sequence choice and all in W3C XML schema, and similar words in relaxing. The control of repetition is by what are casually called exponents or occurrence constraints, optionality with question mark and star and plus for repetition in the usual way. Implementations usually map these regex onto finite state automata because they're easier to work with, and the mapping is well understood except for interleave, which we'll come back to. Published algorithms by Thompson, not me, one of the other ones, and Ao and Ullman from the 60s are the standard reference works here, and they work. But starting with Perl in, God knows, back in the 70s, people started putting numeric expressions, numeric exponents on these things. It doesn't change what you can say, because in principle you can always write 75 A's followed by 37 optional A's if what you mean is between 75 and 102 A's, but it's sort of tedious to do it that way. And in Perl, Emacs and positive regular expressions since approximately forever, often notated with curly braces, so 2, 3, or 4 A's, but it's not trivial to implement. Perl regex code is, if you look at the Perl regex interpreter, it's hugely complicated because it's trying to be as efficient as possible at doing this with checkpointing and backtracking, and not ending up with huge amounts of space. Instead of doing that, when we came to implement this in W3C XML schema, Richard and I adapted the Thompson mapping, the old original Thompson mapping, to handle numeric exponents using unfolding. So here's an unfolded finite state automata to translate a to the n comma m into a finite state automaton. It's just what you would expect. It's n a's followed by n minus m minus n optional a's. And that's all very straightforward, and you feel like that's not unreasonable. And of course, if you've got a star, then at the end you have a loop. It's slightly difficult to see at this resolution, but this edge goes that way and this lambda comes back, so you get as many a's as you need at the end. Right? There's a size problem here. Not just the obvious one that you get n states in this case, but it can grow exponentially because you can put exponents on groups. Right? You can take a parenthesized expression and say, I want this between 5 and 10 times. So if you do that and you take the unfolding approach, you're going to take this machine, which may itself have some very large number of states because of unfolding, and reproduce it m+1 times. And that's not very satisfactory at all. So something like a to the p comma q, b to the r comma s, all of that to the n comma m has order m times q plus s states, which is just not winning. And note that this size roughly corresponds to the kind of size that you're going to have in your checkpoint state if you have a backtracking implementation. Interestingly enough, for the first 3 or 4 years after XML schema came out, we published this paper. Everybody used this approach and pretty much ignored the exponential space problem because, hey, people just didn't write content models that caused the problem. But people started to write things like, there were schemas out there with exponents in the thousands coming from the VR people and things like that. And some implementations, including, I have to say, our own, just ignored the problem and ground slower and slower and slower as they tried to fill memory with these finite state automata. And in the end, most implementations just picked some number and said, actually, we're not going to check above this number. 1,000 equals infinity, right? Once you get to 1,000, we just treat it as a star. And that's not terribly satisfactory. So there's also a problem with interleave, which is there's no straightforward way under the AO and Ullman or Thompson projection to handle interleave. So what I want to do is explain very briefly an augmentation of the basic finite state automaton abstraction to include bounded ranges. And somewhat surprisingly, if you sort of look through the literature on automata encounters, there's a bunch of stuff about automata encounters, but it's not this kind of counter. It's where part of the data space have counters. Right? It's where one of the things you're trying to recognize have counters, not a situation where you're actually trying to count occurrences. And in the full paper of this, I define a finite state automata with numeric ranges and give a semantics for it in a fully declarative way, which is consistent with the traditional description of the semantics of pushdown automata, of finite state automata. But it's actually much easier to describe in procedural style, and that's what I'm going to do here because I want to be quick. So we assume that ranges are going to be implemented as counters. And in order to do this, we're going to decorate transitions with information about counters. And so, and we're going to decorate the transitions in the first instance. So we're going to decorate transitions with a plus sign to mean increment a counter, with a max check guard indicated with a vertical bar, and a min check and reset guard indicated with an exclamation mark. So what that means is that we get something like this. Did I actually click it? Sometimes this takes a while. Let's try again. That looks better. Okay, so there's the automaton for between n and m a's. We use colors to distinguish counters because obviously there may be more than one counter active in a given automaton. So read this as saying, start here, accept an A as long as you haven't exceeded the max. Increment the counter. Accept nothing as long as you haven't exceeded the min. And that gets you to an exit state. This isn't the only way you could do it with these annotations, but it's the way that works for composition, as we'll see in a minute. Right? So that's pretty straightforward. The max check is a strict counter is less than m test, it must come before the corresponding increment. Separating them turns out to again improve the way in which you do composition. And the min check is a test plus a reset if you take the transition, because hey, you may be inside a loop and you're going to come back and start over again. The checks are guards, right? There's no notion of failure here. It just means if you don't satisfy the test, you don't get to make the transition. You have to look for another one. You've several counters for each numeric exponent. So here's what the FSA looks like in the nested case. Right? This is not easy to read, but this is an A with some numeric range, optional B, and then a numeric range on the whole thing. So basically, here's where we're counting A's and maybe B's, and here's where we're counting A's, maybe we get a B, and if we get a B or not, then we can increment the outer loop. So the inner loop is red, and the outer loop is blue. And one of the reasons now becomes clear why it's helpful to separate the guards from the increment is because we end up with the guard on this lambda transition along with the min check for this guy. It's probably too much to ask for you to be satisfied that this actually does the right thing in a short space of time, but I promise you it does. So the only thing that remains is to talk about translation. Well, sorry, there are two things, translation and determinization. Translation is sort of, I have a horrible feeling. Oh, there we are. So an optional term machine needs two new states and a lambda. That's sort of obvious. We're going to use exit transitions from now on. Clingy star is, again, sort of obvious. You take the term machine, you have a lambda and a lambda out. Clingy plus is slightly similar. And this is the generic machine for optional some number of repetitions. And the crucial fact is that the term machine only occurs once. So we've lost the exponential blow-up by using the counter in the obvious sort of way. And we slightly change the topology if the first exponent is greater than 0 for reasons that I don't have time to explain that have to do with checking for determinism higher up. All groups we can now translate. Right? We have any number of alternative branches, each of which allow one of the term machines in the all, that all or interleave. So this says term machine 1, term machine 2, and so on and so forth in any order. Right? But no more than max, no less than min. Today's XML schema restricts the ranges to 1, 1 or 0, 1, but schema 1, 1 is going to allow that restriction to be lifted, and this will cope either way. Simplifying these guys, it is possible to determinize this using a variant on the Aho and Ullman determinization algorithm. You don't change the semantics, but the tricky bit is, given that you're eliminating all the lambda transitions, what happens to all the guards on those transitions and the operations? The closure and the subset is the way you do this, right? Closure of a state by collapsing across lambdas. New subset machine whose states correspond to closures. If you're familiar with this, you know what I'm talking about. If you're not, this is too fast. Don't worry about it. The trick is to deal with the checks and the increments. I'll just show you the example. And if you're interested in this, you can come back to it and look at the published paper. This is another way of looking at a composed machine. This is the the lower level machine, and this is the outer machine. And somewhat surprisingly and satisfactorily, once we simplify it, we end up with a machine with many fewer states. That's obviously not, there are multiple transitions labeled A, but this is a reasonably modest machine and will do what we want. Oh, there's a glitch because it's deterministic. Consider that language, 1 or 2 A's, 2 of those. Right? Well, that actually accepts 2, 3, or 4 A's, but the machine I just showed you has a reduce-reduce conflict, essentially, and it's not eliminated by the simplification. So if we look at this again, consider state 4 in the original. It's probably easier here. At this point, there's a non-determinism whether we, after having found an A, because we're allowed to, after 1A, we could either say, well, that's the end of the first group. Let's try for another one. Or we could say, no, I want another A in the first group. Well, whichever way you determinize that, right, either by being greedy and by saying we'll always take as many as we can internally, or by being modest and always say, well, we'll always take the minimum, you're going to lose with one or the other. If you're greedy, you won't get 2 A's because you'll take both of them for the first go-round and you won't have any for the second. If you're modest and you only take 1, right, you take 1 the first time, you take 1 the second time, there are 2 left and you don't have anywhere to put them. So that's what I just said. The good news is the losing configurations can be detected. You can either have a conservative check, which is very easy, or an accurate check, which requires you to do some number theory and is therefore expensive. But in any case, you can switch to a backtracking implementation which only costs the bad guys. And the bad guys never occur. In all of the schema collections that I've seen, I've found exactly 1 example of this. And it was in a set of documents that were constructed to test the handling of nested exponents. It wasn't a real live schema. It was a schema constructed for the purpose of exploring this space by someone else. I put this into the public schema implementation that Richard and I maintain and that's used on the W3C website. There's an online version of it. It's been out there for a couple of years. As I said, there was only 1 losing configuration that's been signaled, and most recently we put the backtracking in so it's complete. It offers a different trade-off from existing implementations, and I hope the evidence is that people have started to adopt it. Mike Kay has put it into Saxon, which is probably the most widely used commercial schema processor. So that's a very concrete example of where going back to basics, looking at the formal language theory and working at that level gives us something which actually turns out to play out very valuably in the mainstream. I'm going to talk much more briefly about the other 2 topics. Yeah, Ken, sorry, I should have said. Question.
There's a bunch of cases where Early's algorithm happens to be linear time.
Yeah, almost all that we've ever found, in fact.
Let me take a practical example via parentheses grammar.
Right.
And if I had 2 counters, I could do without the stack.
Right.
But all I really need to do is to add one more thing, which is some way to test whether the 2 counters are the same.
Right.
And now I would be taking the formalism you had and taking it out of the generative capacity where it was and putting it into someplace else.
Right.
But it feels like the cases where Early's algorithm's linear time, or at least some of them, like a parentheses grammar, really should be sort of someplace else.
Right.
That it's kind of nuts that one's up there with the n cube case.
Right.
Right.
I haven't thought about that. That's an interesting observation.
Now, I think there are cases where Early's algorithm is linear time, much more general than parentheses grammar. And I'm not sure you could get all of them, but you ought to be able to get some of them.
Yeah, no, that's an interesting question. have to go back and look at that. Thank you. Functional XML, completely different part of the forest, right? Completely different set of questions now, nothing to do with formal language theory. Tim Berners-Lee set me off on this, and Richard, the pervasive influence, had the crucial insight. XML is called self-describing. Mostly this is trivial, right? It just means that you look at the elements, and if you're a native language speaker of the person who designed the element structure, you can sort of figure out what it must mean, right? But it can be much more substantial. When an XML namespace has a clear semantics, that is itself directed at XML. Right? So a number of the XML standards that are out there have a functional semantics. That is, they can be understood as mapping from arbitrary XML to arbitrary XML, typically expressed at the level of the info set, at the information content, at a sort of abstract data model level. So, see talk that I'm going to give this afternoon on the other side of campus about pipelines, about a way of saying, this is the way we want to put, to specify scripts of XML operations. But this is a different take on that, right? There's a bunch of interest in pipelines, which sometimes this slide tool gets lost. Come on, guy. There you go. And there's this processing model working group, which is about to put out a last call working draft of a pipeline language. Functional XML is a completely different approach, which maybe turns out to be similar under the covers. All those pipeline languages have what a friend of mine once called one damn thing after another semantics, right? Very simplified declarative programming semantics. A pipeline is a document which specifies a sequence of operations to be executed one after the other, on other documents, right? So, for example, here's what a pipeline in the Sun stroke markup pipeline language looks like. It says, do X include, then do validation, then do XSLT, right? And the input of this is the output of that, and the input of this is the output of that, and the output of this is the output of the whole pipeline. Right? Unix pipes for XML, fat pipes. Very useful, precisely because in the same way that Unix pipes are very useful. At least some people in this room believe that. Functional XML, a completely different approach. It uses XML's own tree structure to indicate the nature of the processing that the document itself wants to have done on itself. Right? Allow XML documents to indicate their own preferred processing. The superficial semantics of an XML document is its info set, right? Its abstract XML data model. Some XML namespaces specify an underlying semantics in form of an abstract object model that's different, right? So XML schema has this notion of components, and RDF has this notion of a graph, and SVG has this notion of drawables or displayables. And the functional XML namespace is a sort of generic version of this that says, well, a functional XML document has a sort of first order or approximate info set, and then it has a real info set or an ultimate info set. Right? And some other specifications, there are sort of versions of this already. Right? If you have a document which has an XSI schema location on it, you can think of that as saying, you don't really want the info set of this, you want the post-validation info set. You want to validate me and use that. Right? And even seeing an XML style sheet processing instruction at the beginning of a document is a way of saying, you don't really want me, you want the result of applying this style sheet to me. And there's this Griddle namespace which says, you want the Griddle RDF that comes by applying this process to this document, not the document itself. Well, we find these ad hoc signals. Some use attributes, some use processing instructions, some use a namespace that says, I'm encrypted, and the implication is, if you want to work with me, you should decrypt me first. So there are these sort of ad hoc signals that say, not me, but something else. The functional XML approach is to systematize and make universal this notion of documents which signal the processing they want done on themselves. So there are two parts to functional XML. One is an infoset mapping self-describing vocabulary, and the other is a shorthand notation based on the lambda calculus. So very briefly, and I'll get to the point of this and then we can move on. Elements in the functional XML namespace specify an infoset to infoset mapping. Their names indicate what the output is, and their input is the infoset designated by their children. So we use the tree structure of XML to do composition. It's what trees are good for, right? So we've got a simple compositional semantics of the good old-fashioned variety. So consider schema validation and decryption as two kinds of operations, right? We can have an FX document like that, which says, well, FX decrypted of this is what I really mean. Right? So the infoset, the ultimate infoset of this document is the infoset you get by taking the infoset of this node and decrypting it, because that's what the semantics of this node is. Oops. Schema validation, obviously similar. Oops, didn't go. Try again. So this says not this infoset, but rather the post-schema validation infoset you get by schema validating my child. Right? That's what I mean. That's what I really am. And of course, oops, where'd it go? Where's my document? There we are. And of course, it's the power of composition where this thing gets really useful. Either order makes sense. You can say, what I really want is the post-schema validation infoset that you get by validating the unencrypted document you get by decrypting the thing you've got here. Or, alternatively, you can see where this is going. I'm going to skip over the rest of this slide. Well, I'll show this one because it's an obvious sort of thing to say. What I want you to do is check that this is a good encrypted document by validating it. Give me the result, decrypt that, and validate that. So we can nest this in the obvious way. So there's a simple functional language here. The last step that really makes this powerful is to allow you to include X-include, is to include X-include in the mix. So you don't have to always have your document right here. So here's the decryption of a document which is somewhere else. So take the result of running X-include on this infoset, which will give me the infoset of this document, and now decrypt that. So now we've got something that we can really build with. And the science of this is that's interesting. I mean, the place I'm going to skip forward because I'm running out of time, as always happens, right? There's the stuff about multiple arguments. Here are the kind of things you might like to put together in this language. But the compact notation is where this gets sort of fun and starts to cross-pollinate. A functional namespace deserves a functional notation. Fortunately, we've got a good functional notation. In fact, many people think it was the notation we should have used for XML in the beginning. The original computational manifestation of the lambda calculus scheme, we need just 3 correspondences to get us started. Function application of names in the XML namespace correspond to elements in that namespace. A double-quoted string corresponds to X-include, and if you actually put literal XML in, you get literal XML. So here's a little, this summarizes all the preceding slides in 5 lines. Because we've got I've now switched to using lambda as the namespace prefix to indicate that we're using the shorthand. Lambda decrypted of some encrypted data, right? Or lambda PSVI of some document, or lambda decrypted of lambda PSVI, or lambda PSVI of lambda decrypted of that document over there. Right? So suddenly, we've got an XML programming language, quite different from all the other ones that people have been working with. Right? So, here's a style sheet application of a multiple argument case, where lambda colon result, which you haven't seen before, means the result of running XSLT on this info set using this info set as its style sheet. And where this gets fun is where we start trying to, we start to back import it. And we say, well, gee, there are these useful forms, these special forms in the lambda calculus or in Scheme for doing conditionals and for binding. And something like this then becomes a very powerful backport into the notion of a compositional XML language. So we say, well, we can have a cond where there's a test on this info set and this XPath. So we introduce one more bit of notation, square brackets for XPaths. Right? This slide seems to have gotten slightly out of sync with itself. We could use lambda test like this, or we could actually introduce binding and allow variable references in XPaths to refer to things that are bound. So now we have a variable bound to an info set, and we can test that info set and run schema validation using one schema or another, depending on the result of that test. So, a sketch of a little lambda calculus programming language which translates directly into, whoops, something on that slide I want to mention, which translates directly into this compositional XML language. Have to be very careful with binding. When you introduce binding, you introduce the potential for recursion, and I've chosen let very carefully here, meaning that none of the things bound here are in scope for the binding, so you can't have recursive bindings. So at the moment, this is all still just simple recursive descent evaluation, simple compositional semantics. You could do mapping if you were really so inclined, but I think that's going too far. I think I'm done, if the machine will get me to the last slide. It's worth noting that raw XML is not so much quoted as back-quoted, because you want it to be the case that in the middle of raw XML you can switch back to computing bits of stuff, right? So you can wrap things. I thought I'd drop these slides. I'm sorry. I thought I'd gotten rid of them. Functional XML faces two directions at once. It's a novel approach to self-describing XML as an alternative to the sort of linear scripting kind of pipelines. And that's just the sort of normal duality, right? It's often the case that when you have a functional language, there's a sort of procedural dual that you can convert back and forth between. But it's also this sort of interesting candidate for a programming language, which is very different in style from XQuery or XML Lambda or Lynx or any of their predecessors out there in the XML programming language space. And I've got a PhD student who's sort of exploring this, particularly in the context of web services, where composition of web services is something that you want to have a language to express. And this looks like maybe being a good way to do it. Well, it's 10:15, and I had one more talk, but I'm not going to give it. I'm going to extract one slide from it, because to suggest that people who are interested in this topic might want to go and look at this part of the talk.
Are these slides available on the web?
They will be. I only finished them on the plane last night. Needless to say, these are all extracted from longer talks, and I'll put both. I mean, the version that I'll send it to you, Ken, so you can put it wherever people would expect to find pointers to it. So there's this interesting parallel between a difficulty that people have with expressing just what it is that URIs are about, this notion of resources, and some fairly fundamental issues in philosophy of language. So there are some parallels between these two which I think actually are illuminating. Who gets to say what the resource is that a URI is about? Well, the person who mints the URI. It's up to them. And who gets to say what a word in natural language means? Well, we don't do new words all that often compared to the number of old words, but in principle, the answer is the first person to use it, the coiner. It's sort of interesting that the metaphorical domain is the same. We talk about coining words and minting URLs, and they're both from that very odd little semantic domain. I don't know why. The web standards involved here, both the RFCs for the URI space and the web architecture document from the tag, talk about URIs as identifying resources. Well, what's a resource? And the documents say anything at all. Concrete, abstract, imaginary, real, not real, whatever. Similarly, in ordinary language, philosophy of language, we say, what can be referred to with a word? What's a referent? Anything at all, right? So people who criticize web architecture by saying, you haven't told me what a resource is. You haven't told me how to distinguish between resources and anything else. Saying resources could be anything at all is vacuous. It's useless, right? Nope, that's a bug. Things are resources just the same way things are reference. Not because of anything intrinsic, but because someone minted or coined a URL or a word to refer to them. That's what makes something a referent, not anything that it is itself. Right? Some people find that analogy helpful. The other parallel, which I'll finish with, is there's a hugely important subset of URIs which are deictic, which are indexical. Right? So things like localhost and file colon, all file colon URIs, right? These don't have fixed meanings. Well, they do. I'll explain in a moment. But they don't have fixed reference. Right? They mean what they mean differently on my machine and your machine. And other URIs are indexical in a different way. Right? The homepage of the Guardian newspaper, that's what that URI refers to. That changes almost moment by moment. It's not fixed in time. And the relevant specs go to huge difficulty to try to get a handle on what it means to refer to something which isn't stable. And they don't have the language for it. But we do. Right? I mean, there's this sort of useless phrase. They could use some help. Right? We know how to do this in the philosophy of language. We've got this distinction between meaning and interpretation. It's been around for 30 years at least, and in some ways it's been around for over 100 years. So it would be so much easier if they could just say, URIs have a single meaning, but multiple interpretations. Right? Meanings are a function from context to interpretation. What is the context? Well, it's the time of dereferencing and the circumstances, the machine that you're running on, and the nature of the proxy space, and a bunch of other stuff. Right? It would make the whole explanation of this aspect of the semantics of the web much easier to talk about if they imported this notion from the philosophy of language. So in general, there's a whole little research program running in a fairly informal way between various places, including Edinburgh and Pat Hayes in Florida and various other people, to try to sort of reanalyze the philosophy of the web. You know, wherever there's good science, there has to be philosophy of that science to tell you what it is that you're doing. And to try to actually rationally reconstruct the ontology in the real old-fashioned sense of the word ontology. What are these things and how do they function? Is the web a logic? What kind of a logic is the system of names and references that the web is founded on a logic? And if so, can we use the terminology from philosophy of language, from logic, to help us understand how this whole system works? So there's a research program running there, which I think is bearing some fruit. Thank you for bearing with me through this Cook's tour. There's probably been nothing that's been of interest to all of you, but I hope there's been something that's been of interest to each of you. And I'm around until lunch at least in this building. I'm happy to talk to anybody who would like to pursue this further or to answer questions now.
Anything you're talking about has anything to do with the semantic web? That people talk about 3.0?
Yeah.
What's the connection?
So a lot of the motivation for this last thing, which I spent the least amount of time on, is specifically to address the following question, right? Some of the people in this room have been around long enough to know that knowledge representation has a long history in AI and a long history of grand hopes followed by modest successes. And one of the things which a lot of people in the AI community have responded, the ways in which the AI community has responded to the semantic web program has been to say, you guys haven't done your homework. You don't know what we've had, you know, the burned hand fears the fire. We've been there, we've tried to do this, we've failed. What makes you think you're so good? Right? We've seen this before. People come in from outside and they say, this knowledge representation stuff can't be all that hard. We can crack it. Right? Well, there's only one thing that's different about the semantic web program, semantic web technologies as they're emerging, from all the other knowledge representation systems that have been around since, you know, have been developed and tried, beginning in the 60s with first-order predicate logic, essentially, in the lambda calculus, and the knowledge representation systems and semantic net in the 70s, and so on and so forth. You know, you can fill this in as you go up through the decades. There's one thing that's really fundamentally different, which is that the semantic web story uses URIs for all names, for all properties. Everything is identified with a URI. Right? Otherwise, it's pretty impoverished, actually. It's just relational triples. You know, two-place predicates. That's it. You know, two-place predicates, constants, and URIs. That's all you get. All right? That's not much of a knowledge representation system. Why do you think you can do any better than any of the rest of us have been able to do? Well, if there's any value at all to that, you know, if there's any plausibility at all to that claim, it comes from the expectation of the network effect. We all, you know, the network effect is why the old-fashioned web took off, right? Why it got around the exponential, the knee in the exponential curve, because, you know, your website and my website developed completely independently about whatever it was that we were interested in. You find each other through a search engine, you cross-link to each other, and everybody wins, right? Can the semantic web do the same thing? Can we get the network effect for machines communicating with each other on the web? Well, only if they have a shared vocabulary. You know, the old-fashioned web has a hidden dependence on natural language and human beings' ability to understand it. The semantic web depends on being able to take independently developed ontologies, now with a lowercase o in the semantic web usage, and detect that they are about the same thing and figure out how to merge them. And that is possible, if it's possible at all, only because they're using URIs which admit to the follow your nose principle. If I come across a random bit of any other form of knowledge representation, I have no way of finding out what the terms in the equations or the networks or whatever else it is means automatically. But if I come across a fragment of RDF which says, you know, Beethoven is a composer, and I have no idea what any of these things mean, I can dereference those URIs and find more RDF. And following that process repeatedly may and the promise of the semantic web is will get me to something that I do recognize. So the whole issue of naming and the way that URIs function on the web to identify both concrete, representable things like the front page of The Guardian and the weather report for Seattle, but also to identify but not retrieve directly things like Seattle itself. The debate at the moment is about, well, how do we, what is the distinction? Is there a distinction? And if so, what is it and how do we exploit it, represent it, and be careful about it between the Seattle Weather Report and Seattle itself? And web architecture, web ontology has not got a clear answer to that question yet. And until it does, the whole semantic web program is sort of teetering, right? Because it depends crucially on that kind of distinction. So yes, very much so. This last story, this last issue does connect up very much with the semantic web. Sorry, that's a long answer to a short question. Now I know which talk I should have given. Ken.
So you got a bunch of hats there, and mostly I think you've been talking about the last hat, but let me ask you to put on the first hat.
Yep.
And let me go back to the sort of problem statement you stated at the beginning, which is you're in this room, and there's a couple of people who remember the way that the issues that used to be popular when we were in graduate school, but most of the people, or many of the people in the room, have another set of agendas, right, and another background, and may or may not have been exposed to that set of issues and whatever. Okay. Now, what I'm wondering is, as a community, what are we teaching the next generation, and how many of the topics are you describing here are no longer really in the curriculum?
The formal language theory stuff, absolutely not. Right? I don't know. Maybe I asked my son, who'd just been through the first year of computer science at York, which is one of the better schools in Britain for computer science, what they had learned about formal language theory, and he said he hadn't heard that word. And so I asked him about finite state machines. He said, "Oh yes, we had a lecture on finite state machines." And that was it. Right? But I don't know how. So how many people do you need to do compiler theory, right? I mean, we don't need thousands of compiler theorists out there.
We need enough to win the debates in these committees.
Yes, right. That's right. And I think the formal language theory stuff rarely impacts. I mean, every once in a while people do things where you need to be able to say, actually, that's NP complete. You don't want to go there, right? They propose to do things in that space, and then you do need to say something. But that's very rare. And if you don't say it...
Your lectures are of this form,
right?
Right. And maybe it's the problem is that we're not teaching the next generation the issues you need to understand this debate.
That's probably right. I think the place where it's most vivid, however, is the semantic web case, where the knowledge representation, the AI community, the knowledge representation community, the people who are presumably still being taught. I know that in my own institution, for instance, people are taught the history of knowledge representation, and they learn a bit about Quillian nets and semantic nets and KRL and clone, and because the descendants of those are still with us, right? I mean, and production systems. So people learn about that stuff, and they learn some of the complexity results are still coming on those things. And it doesn't take, again, many people to worry about that stuff, but you do need to know that they're there. And the problem is that the web community has developed almost entirely autonomously, and is by and large made up of people who who are self-taught or come from other disciplines. And I don't know what the consequences of that are going to be downstream. As it says in one of the slides I didn't get to, one of the reasons why the technical architecture group of the W3C is important is that we're trying to, with 20/20 hindsight, figure out what it is that makes the web work. What are the properties of the web that it depends on, so that we don't break it inadvertently, right? So that we don't discover that some new line of exciting work doesn't inadvertently end up trashing the foundation of what makes the web actually succeed. And so one of the, and the fundamental role of URIs as the naming mechanism for the web is at the heart of that. So there's been this huge debate, for instance, with the web services community about these things called endpoint references, about the use of little chunks of XML to identify things, which you can't write on the side of a bus, which you can't give to any browser and get and follow your nose. Right? How important is this? Does this really matter? The 3D environments that are growing up. Right? So I don't know if any of you know about OpenCroquet, which is this sort of 3D browsing language, the language for creating 3D spaces that link to other 3D spaces. They could have, but they don't, use URIs to name microworlds, the things that you author. Right? You author a web page, you author your own microworld. It's very similar. You do it by pulling together bits and pieces that are already lying around. But when you want to link from your microworld to mine, you don't use a URI. You use a little chunk of XML. Right? So sending it around and getting it interpreted have a completely different dynamic. Is that the right thing to do because the problem space is different? Or is that the wrong thing to do because you're missing the network effect by doing that? I don't know, but it's worth worrying about. Bob?
All right, going back to your first talk, can you just, I found myself wondering, well, why does the W3C consortium think it's important to formalize all the bad HTML and XHTML out there in the world? Isn't it enough to say, here's a standard for doing it right, and a kind of a safe harbor approach? If you follow this clean standard, you can be assured that basically all the browsers will render what you've written correctly. If you go outside the standard, you're on your own.
The answer,
which is not the same as the first thing you said, which is if you go outside the standard, the browser screen will be blank.
right, understood. And that's certainly a position which was argued. It took about 18 months of debate, both internal and public, to get to the position where 6 months ago the new working group was chartered on the basis it was chartered, which was the basis I described. That is to standardize to standardize the browser's recovery behavior, to standardize TagSoup. And essentially the argument which won that debate was the W3C exists to serve its members. The W3's activities serve its membership primarily by promoting interoperability of their products. What we need in order to promote interoperability of our product is this. And that's why all the browser vendors are on the committee when they weren't up until a year ago. Right? Up until 6 months ago, they weren't. Right? One of the reasons that from the W3C's perspective, this crisis came to a head was because we had successively lost virtually all the vendors from the ongoing development work on HTML because it wasn't addressing what they perceived their needs to be. And this does. What you suggested works for me, and it's an absolutely classic case of what happened, the week after we announced the working group and its terms of reference. A significant number of constituencies, not just individuals, but constituencies, suddenly perked up and said, what? Wait a minute. What's going on? We spent the last 3 years converting everything to XHTML, and it gives us huge value, and now you're abandoning us. And we said, where were you a week ago, a month ago, when we were having the debate about what to do? And the answer was, well, they were doing just fine, thank you, and they didn't think they needed to do anything. Right? And it does remain to be seen whether we need to do something else as well, along the lines that you just suggested.
So what does your company Markup Technology Limited is doing?
Oh, Markup Technology was a company that built a pipeline engine 5 years ago, and unfortunately it was at least 4.5 years before its time. So we never got follow-on funding. But it still bumps along, and we may yet manage to get an implementation of the new W3C pipeline language out, even if we have to give it away, because we've got this lovely code base. It's an order of magnitude better pipeline engine than anybody else has ever built, and it's a shame that it's sitting not doing anything. because we never got the money to finish the higher levels of it. But thank you for asking. If you need a pipeline engine, I'm your man. It's 10:30. Thank you very much.